I'd just like to add a few more examples of derivatives of trig functions. So in this example, we have r equals secant theta times cosine theta. In order for us to find the derivative, we need to recognize that there's a multiplication in here. That means we're going to use our product rule. Now remember, the product rule, derivative with respect to x of some first times a second, would be first derivative of the second plus second derivative of the first. So in this case, the derivative of r with respect to my independent variable, that theta, I'm taking the derivative of r with respect to theta. That would equal my first, which is secant theta, times the derivative with respect to theta of cosecant theta, the second, plus cosecant theta times the derivative with respect to theta of the first, which is secant theta. So we have secant theta. What is the derivative of cosecant theta? That is negative cosecant theta times cotangent theta. And that we know, right? This derivative is one that we know. Plus, we have cosecant theta, and the derivative of secant looks very similar to this. It's going to be secant and tangent, and it will be positive. So we have secant theta, tangent theta. At this point, we are completely done taking derivatives. We do have a lot of reciprocal functions here, and we need to clean this up. Probably one of the easier things for us to do here would be to turn everything into sine and cosine. So, the derivative of r with respect to theta is still what we have. Secant is 1 over cosine theta. I'm going to move that negative just into the front here. Cosecant is 1 over sine theta. And tangent is cosine theta over sine theta. Plus cosecant is 1 over sine theta, secant 1 over cosine theta, and tangent is sine theta over cosine theta. So we see some nice canceling. In that first set of multiplication, the cosines cancel, and in our second set, the sines cancel. So we can simplify this and say that dr d theta is negative 1 over sine squared theta plus 1 over cosine squared theta. And that's perfectly acceptable as our answer for the derivative. I do like to clean it up a little bit. And since we started with our reciprocal functions, I feel like it's okay to end with them here. So dr d theta, cosine squared, that's the same as secant squared. And sine squared, I'm going to move them. Sine squared is the same as cosecant squared. All right, so I just want you to notice sine came over here because I wanted the negative in the middle, and cosine came to the front. The reciprocal of sine is cosecant, the reciprocal of cosine is secant. Because they were squared, that remained. And this is really as far as we can go with this problem. So my derivative here for secant theta times cosecant theta is secant squared theta minus cosecant squared theta. And looking at that, I think, well, do I know any identities? That looks like it could be related to a Pythagorean identity, but it's not, so we can't simplify any further. For our second example, we're going to find the second derivative of y equals cosecant x. So this isn't really a difficult problem. I just want to show you that you can find higher order derivatives of trig functions. And one thing you would notice, especially if it was sine and cosine, is they can become cyclical, where they repeat themselves, right? Because the derivative of sine, if we think about sine of x, and we were taking the derivative of sine is cosine x. Well, what's the derivative of cosine? Negative sine x. So if I were to take the derivative of negative sine x, I would get negative cosine x. And differentiating that would take me back to sine. So we have kind of a circular pattern that would happen there. And after the fourth derivative, we would see, okay, well, we're starting over back at the beginning. All right? So that's not quite the case with cosecant, because cosecant's derivative isn't as nice. But we'll look at finding the second derivative here. So my first derivative, the derivative of y with respect to x, well, we know our derivative for cosecant is negative cosecant x cotangent x. This represents my first derivative. So if we want to find the second derivative, that would be the derivative with respect to x of the first derivative. And just emphasizing my notation here, we would write that as d2y dx squared. Okay, so my second derivative, when I go to find that, I need to use my product rule. First, derivative of the second, second, derivative of the first. So I'm going to work this out just a little below right here. So my first, I have negative cosecant x times the derivative with respect to x of cotangent x plus cotangent x times the derivative with respect to x of negative cosecant x. So what we have, I've got negative cosecant x. I know the derivative of cotangent is negative cosecant squared x plus cotangent x, and the derivative of cosecant is negative. So the derivative of negative cosecant would be positive, and we would get cosecant x cotangent x. At this point, there's just a minor bit of simplification. Multiplying these first two would be positive, and I would get cosecant cubed. And for the second piece, I have a cotangent squared times a cosecant. So I would write here plus cotangent squared x cosecant x. And that could be my final answer. Of course, I always like to look and see if I can factor more. So in this case, I could factor out a cosecant x, and that would leave me with cosecant squared x, cotangent squared x. Either of those are fine as my second derivative. All right, so I hope that helps you a little bit more with understanding repeated derivatives as well.